Okay, so I got a little sidetracked doing this drone power supply project. And the reason for that was because I really don't like the way that actually the choice of footprints that KiCad provides, and I don't like having to look for the right footprint for every single component, and I don't like having to scroll through really large lists of different footprints that are not named according to any well-defined standard. So I decided to create a set of scripts that would generate all the necessary footprints for this schematic, and I ended up with this. So this is all the footprints that are automatically generated using my scripts, and I'm going to explain to you why I like this way a lot better than the default KiCad way. So first of all, let's go ahead and copy this board so that we save it, and then I'll show you what it will look like if I import the default KiCad symbols. Let's see. So I'm just gonna close this, and I'm gonna just make a copy of this board. Let's see. I'm going to delete the existing PCB, and then I can just go to the PCB editor, and it says that I didn't create the board yet, so I get a clean slate here. So let's just go ahead and import. Let's see, can I get the window? Oh, it just appeared on the. Let's see. So there. So let's just go ahead and synchronize this. So update PCB from schematic. Now, oh, I just realized that this is not going to work because this is going to actually import my footprints. I would need an older version of the schematic to be able to do this. But let's just go ahead and try to import the KiCad footprints side by side. So I'm gonna copy the file back. And I'm just gonna go to the schematic editor. So for example, let's look at one of these capacitors. I can place a footprint for one of the capacitors. Now in the datasheet it says it's 1210 capacitors, so we can go to capacitors SMD. Let's see, capacitor SMD, and usually, and this is like everything is all mixed together, and sure, there is some kind of system for naming the footprints, but generally in KiCad there is no well-defined way to name the footprints. And the worst thing is that I cannot just type a string into, like, I cannot just assign a footprint and then get it generated. I have to, there are some scripts to generate the footprints, but they're not part of KiCad. They are part of the KiCad footprint generator project, which is a different project which I actually use as base for my footprint generator. But the difference is, what I really like to have in KiCad is the ability to just go to the schematic. So let's see. This doesn't seem to really work. I cannot switch to this. Let's see. And I go to this. This is actually a new feature in KiCad 5, which is let's see. Is there a dialog somewhere that I do not see? Yes, I have to close this dialog. Right. So this is a list of all components, and I think the idea is I really like this feature, by the way. I think the idea is that you can use this to kind of set the values and ensure that all the fields are correct and all the packages are correct, and you can actually edit things in this list, and this is what I really like. So I usually remove like description and datasheet and just leave like the most essential fields in this list. So here I can select the footprints by just typing strings. And what I cannot do this with KiCad footprints because I can never remember exactly what the footprint is called. So if I were to like type here, what was it called now? Like capacitor what? And I have to close this dialog and I have to go to the library and pick the footprint, which is like really annoying. Right, so if we go to the browser here, you know, I would never be able to type this name manually because this is like not a well-defined name. So how can we do this better? Well, there is a standard called IPC standard, which defines exactly what the names should look like, and it defines a standard framework for naming components. So if we were to look for this capacitor, by the way, that is a chip capacitor. I'm just gonna do what I was gonna do originally, and I would just import this footprint. Let's see, I will just import this footprint side by side to my generated footprint. If I were to, let's see, if I go back to this PDF document. So there is a well-defined convention for naming footprints. And the capacitor that we just added was a chip capacitor. So capacitor chip, not non-polarized, are defined to have these names. So this is a footprint name for a capacitor, which is a chip capacitor, non-polarized, with a body length and body width times height. And this is really all you need to generate a default footprint. Sure, there are different other parameters that you could set. You could set the distance between pads, and you could set the width of the pads, and like the distance is from here to here, and you can set the width of the pads, the width, the length, whatever, solder mask, whatever. There are other options, but the essential options that you need to know about a capacitor is just this. So if KiCad footprints were named like this, it would be really easy. I could just then go to this dialog that I have in the schematic editor, and I would just double check that all the footprints are correct here. And essentially what I'd really like to do is to be able to synchronize this with the library, with the component library that I'm using. Because you know, even the component library management, I really don't think that KiCad has a workable workflow for component management. There was a discussion on the GitHub account, I think, for the libraries, where somebody wanted to like create distinct components for every single diode that was produced by Vishay. And then the developers pointed out that that is not going to be feasible because there are like 250,000 of them or something. There was like a really large number, and if you were to generate all of those diodes and put them in a library, the KiCad wouldn't even load because it's going to be so many components. And I don't think that's the correct way either. I think that the official KiCad library should be seen as a template library. So all of the components that you have in the official KiCad libraries should be just templates for standard components. So like in a lot of ways that's already the way it is, but I don't think that people view it that way by default. They don't see this as a template library, rather they see it as a library of components they should use directly in their schematic, which I think is not a very good workflow, and in fact it's a very bad workflow. Because what you want to be able to do is to look in this official template library and to be able to right click on a component and say like, I want to use this symbol for a component of my schematic, and then I want to specialize this template for my schematic or for a set of schematics. So in order to be able to do that, you have to be able to easily copy this component into a custom library which is either local to your project or local to a number of projects where you share components. And then you specialize this component, and this is exactly what I've done with all of the components on this schematic. So if I look in this resistor and I choose like to edit this component with a library editor, this is a distinct component in my project library. And the reason I do it this way is because you have to do it this way in order to be able to each component to a distinct part. Basically to a manufacturer number, but it could be more than that. But the most basic thing you need to do in a project, and which is not doable through the official libraries, is to be able to specialize a component and to say that this is the component that points to this particular part. For example, this capacitor, if we open it and we edit this component, we have in the fields for the component, we can see that this particular capacitor points to this particular serial number, which points to an actual product in the at the supplier. So this is actually a manufacturer code, but I can search in Mouser and find this component. So I can find this capacitor, and I can double check that it's correct footprint, and there's a whole bunch of different fields here. And the ideal way in KiCad would be to be able to import this this set of fields automatically from Mouser or from DigiKey or from any other supplier, and to be able to then choose the template from the official library that I want to use. So for this capacitor, I would use the capacitor template. The non-polarized capacitor template would be just the C symbol, or like C small, which I'm using here. And if there was a way to search Mouser components, there is actually an API in Mouser. So you can actually make queries into Mouser database and get all of these fields supplied as an XML document. But you need to have an account, which is free. You just register an account, and then you can get access to their API, where you can search for products, get how many they have in stock, get any other parameters for a component. And ideally, what I would like to do, what I would like to be able to do in KiCad, which I'm actually looking into adding to KiCad as well, because it's all open source, is to be able to make those searches directly from KiCad, and then to be able to import all of these fields, because it's completely unfeasible to import those fields manually, to like enter every single field manually into this particular specialized template for my component that I use in my schematic. But it would be really nice. And another thing that is currently missing from KiCad is an easy way to sync with libraries, and actually to sync fields with libraries. So what KiCad can do is sync the visual representation of the component with the schematics, but there is currently no easy way, at least I haven't found it, to synchronize the component in whole. So I just want to be able to, like right now, what I need to do is update field values, and then I have to actually manually click like value, for example, which would be the name of the template, and then I have to click OK. But even just this step of having to go into every single component and click update field values, when that can happen automatically, is just an extra step, which is like really time consuming and error prone. Anyway, so what I usually end up doing is specializing all of the default templates that KiCad provides, and creating components that are specific for my schematic. And I also add, for example, for this resistor, I've added the value of the resistor as text in the component, which ensures that I cannot change this value. And this value should never be changed. Like the reason I think that this is not that KiCad hasn't really understood this way of working is because the value of the resistor is actually the name of the component. So the value is like the same as the name of the component. And the idea is that you then go into the schematic and you change the value to something else. But that, unfortunately, that is local to the schematic. So if I were to show this value, for example, if I show this field, so this is what would usually happen in KiCad, is that you import the default symbol, which is a resistor, and then you get like an empty field here to fill out with the resistance of the resistor, like that would be like 523 K 1%, right? And that's how it would usually work with KiCad. The problem is that if you use the same template for every single resistor and you just change this string here, then you cannot have links in your library, which which you just do once and then reuse in every single schematic. You cannot have those links saved in the library. You have to have them locally in your schematic. So you have to do the specialization of each component locally in the schematic, which I think is both error prone, and it's actually a lot of double work that you have to do for every single component, when instead what you can do is just specialize it in the library and then duplicate the same component and know that the manufacturer field is always going to be there and it's always going to be correct. And any other fields, like if there was a functionality to import components directly from Mouser, then typically I would have all of these fields, all of this already imported into the fields here. And even though this is this dialog currently points to the instance of the component in the schematic, it would be the same dialog when you edit the library symbol, right? And with the functionality of easily being able to synchronize from the library and into the schematic and replace all the fields on the schematic components, it would actually be a very straightforward and very robust workflow to define your specialized templates for each component, and then to reuse them in different schematics, and to be able to just make an update in one place, which is in the library, and then update all of your schematics using just a simple button press somewhere here, like in the toolbar, if there was a button to synchronize all of the components. Like, let's see actually if they've added it. If they've added any, like, let's see, find and replace text, redraw schematic view. So usually this, I think, would import the graphic symbols for the schematic. So let's try to change something. Let's see. I'm actually curious if this will work. Let's go here, properties. And then let's change both this and let's see, that we're never going to see that. Let's try this. And then let's change one of the fields. So let's add a field. And then save this component, and then let's go to the schematic and try to redraw. Okay, so it has redrawn the view, but I don't think that the field are, no, see, the fields are not here, so I have to press this update field values to be able to update the fields, and I don't think there is a button anywhere to be able to do that. Like tools, symbol table, I don't think, I've never seen that anywhere here. Oh, look at that, that's actually there. That's interesting. So it did have that. Maybe it actually even had that in an older version. That was really cool. I didn't know it had that. That was really cool. I love this. But unfortunately, I don't think there is a way to update back. Let's see, can we do this? Can we change this to like something like that and do like back? Right, no, this is something else. This is for footprint association. Can we do this? Let's see, because now I messed up my footprints association. Let's see, I have to close this. Let's see, can we do back annotation somewhere here? So how do you actually do that back annotation that they have a function for in the schematic editor? This is quite interesting. Let's look this up. Let's go here and do KiCad back import. So, is there a function somewhere to export, like, export? Oh, there we go. There we go. Export footprint association file. Cool. So then I can go back to the schematic and I can actually back import this. So there is a button for this. Like, let's see, show all footprint fields, hide all footprint. Like, let's see. Yeah. Cool. So there is a button for this, but there is no button for like updating all the fields. Like all the fields, field update is like here. Okay. Anyway, so I think that this now should have the right. So now it has the correct footprints. Unfortunately, I don't think that there is a way to back import this into the library editor. Can we see if there is anything like that? Edit footprint, edit with library editor. Now, is there a way to import fields from the schematic? Because the problem is that what I would like to do and what I've done on the schematic is that I would actually go into the dialog here, this new dialog, and I would actually modify things here. But this modifies things only on the schematic. So I would actually go like and double check. I would go through every single component. I would copy this manufacturer number, and then I would go to Mouser, and I would search the component, and I would just check what kind of height it has, for example, what package it has, and you know, any other parameters that are interesting for the footprint. And for example, here I've manually entered many of these footprints where I would say like, okay, the package has 0.4 millimeter height and it's 1.6 times 0.8 millimeters chip resistor, right? So then I could just enter this string, and what would be nice in KiCad is if it could generate this automatically, but what I ended up doing is writing a few Python scripts that would generate those footprints for me. But what would be really nice here is to be able to modify this field in the schematic and then to be able to import it back into the library. So so that in the library, I would not have to go into the library and redo the work, but I would be just able to do it through this really nice new dialog there. But that doesn't seem to be there. Maybe it is present in like somewhere where I cannot find it or something. Let's see, let's modify this back to what it was, and I really like the fact that it automatically updates the symbol. It didn't do that in previous version. Like in previous version, what I had to do was actually click on this button to place a symbol, and then I would like place any symbol, and then it would update. But in the new version, in the version 5, it updates it automatically when you save the library. So that's really nice. So really cool. Now, so let's say that we went into this dialog and we went through like components here, and we have the standard footprints, or actually, oh, forget it. Let's like totally forget it. So this is just the KiCad way of doing it, and I don't really see this as the perfect way of doing it. So what we usually do is like go into the library. So I would open the library editor, and I would go into my local project library, and then I would like click on every single symbol, and then from here I would set the footprint. So it should be correct once you create this library. You should have all the fields correct. But what I really mean is that it would be really nice if in this other dialog here I would be able to back import the fields into the library. But I shouldn't be using this dialog right now for assigning footprints, because that functionality is simply not there, right? So let's say we create a new capacitor, and let's say we will go to Mouser and pick any capacitor, and we know that it has a certain width and a certain length and a certain height. So the proper way, which I see would be the simplest way to create a footprint for this capacitor, is just from this simple text string that represents the chip capacitor footprint. Now here I still have the old values, so this is probably like not right. This is a 0.9. It's 100 nanofarads, right? So it's about 0.9, I think. And I have to go back and I have to go through every single component here and reassign the footprints to correct ones, which is quite tedious. But anyway, so how do we actually generate those footprints? And I've created a set of Python scripts based on the KiCad footprint generator to create those footprints from simple CSV files. So if we go to our capacitors here, I have a bunch of footprints, and all I have to do here to add a new footprint is just to add a new line to this file. Have this horrible cold that just wouldn't go away, and I find like my voice is getting really... I'm starting to lose my voice because this cold is horrible. So if I want to add a new capacitor of whatever size, I can just do it very simply by using this wizard. So like if there was a capacitor 4.5 millimeters times let's say 6.5 millimeters and a height of 3 millimeters and board density normal, it would just be a matter of adding a simple line to this file. And if there was functionality in KiCad to be able to automatically generate footprints, it would be just awesome. You just enter this footprint and it generates a default footprint for you. So let's run the script and let's see what our footprint looks like. We can do it by just opening the footprint editor. Let's see. And then opening the component in the footprint editor. So go to Cap C, and then we have 45. Let's see. There it is. So if we had a capacitor that had this size, it would have this footprint. And this basically uses like some default assumptions about the size of the pads, but usually that works. Like for the most part, this would be very similar to the actual official footprint for this capacitor, and we can go and search for let's see. I mean, obviously there is a tolerance there, but like if you open, like if you go to capacitors, ceramic capacitors, and see if we can just find something that has some footprint we don't have. Let's see. Like 4040. Do we have any capacitors that have 4040? 3 of them. We can open the datasheet for this capacitor, and we can see what the actual chip looks like. So here is 4040, and do we have any? dimensions for it. It could be that it doesn't really even have the recommended pattern, like recommended landing pattern. No, it doesn't seem to have that. But the 40-40 part itself is like, let's see. So 40-40 in metric units, what would that be? Let's see. That's a pretty large footprint. Like that would be 10 millimeters. So like 101. That's not even workable. But we could try that. We could try that because the particular interesting thing about this is that it's going to be like 101 times 101, and I don't think I have to actually double check if I've added support for that. If my parser supports, let's see, parser for the chips, if it supports the large string. Yes, it does. Okay, cool. So this should work. So what would be the footprint for this capacitor? It will be in metric units 101 times 101, right? So we can just easily enter this footprint into our list of footprints. Let's see, I'll just open those footprints using a spreadsheet viewer. Let's see, I can open it in OpenOffice. So if I go to this KiCad footprint generator folder and let's see. So if I look in the footprint generator folder, where I've added new files, this like the different generators for different components, and then I've added this data folder. So it already has some scripts that generate different standard libraries for KiCad, but I really don't like this way of generating libraries. Like every single generator is a different story. Like and if you need to change anything, you have to go into the scripts and modify them. I really don't like that. So in my way of generating these footprints for this schematic is that I've just generated, like I've written generic generators for chip, molded, and SOIC, and then I've just created this set of CSV files where I can add new footprints. So let's see if we can add our capacitor to this list. So the way this generation works is that we can just, the only thing you need to do to create a new footprint is just add a row to this file. So our new footprint will be called like capc 101 101 and times what was the height of this thing? Let's see, the height is t, thickness 4040 0.3. I wonder if this is okay, right. So it actually already provides the measurements in millimeters here. So 7.62. So let's see. Come on. Did it end up on the other screen? Right, there it is. So 7.62, we could say like it's 776. And n is for the the courtyard around it. So actually this would be 102 according to the datasheet, right? And then all we have to do is just run this script generation, and we will have our new footprint in the library, and we can just easily assign it to the new component in the library, and then we can just use it. And let's see what it looks like. So let's see what it looks like if we add it here. So we can just place it somewhere. Let's see. So where is it? Oh, did it not generate it? Did something go wrong? Could be because the size string is so long. Well, this is good. I can actually debug my scripts and check what is wrong. Let's see. Did it not end up there? No, it doesn't seem to have ended up here. So what happened? Did I forget to save it? That explains it. Let's see if it ended up here now. So this is our new footprint. We can add it to our schematic, to our PCB, and then I would just open it in 3D viewer. And this is what it looks like. So I've generated both a footprint and the 3D model using Python script. And I really haven't bothered to like create anything fancy here, so I just create the boxes that kind of basically bounding box for the component. But it's good enough. It's good enough for what I'm doing right now with this particular PCB. And if anybody feels like adding more complex 3D models and generating them automatically, it's perfectly possible to do that. And the way I'm doing it in this generator is through the FreeCAD Python interface. So if anybody doesn't know it, FreeCAD has a Python interface which you can import like this. So here I have added the path to the FreeCAD installation, and then I can just import a bunch of different Python libraries. And then I can, in this particular case, I'm just creating a box. So I'm just using the part library and make a box and set the width and height of the box and then scale it. And the scale is 1 divided by 254 in order to get it into the scale that KiCad uses for the 3D models. And then I export this model as a VRML file, and I can actually also export it as a step file, but I haven't done it right now because it kind of requires loading the GUI, I think, from Python, the actual FreeCAD GUI. So it's not really trivial, and like exporting the different export functions in FreeCAD, they're actually located in different modules. So it's like, well, okay, it's really not organized the way you would expect it to be organized. But the good part is that in FreeCAD, when you actually open FreeCAD, you can see all of the commands that it's executing, all of the Python commands here. So like if you change the size of this box, you can actually see what command you need to run to be able to set the size of this box. Like this was not the size; this was actually like the rotation of it. But you get the idea. So like the length we can set to 1.58, and the way you do it, it shows you exactly how to do it here. So obviously you can do more complex things like chamfering the edges and adding more features to this box, and you will see exactly how to do it here. And then you can just copy it into this script and generate the model, and then the model gets written to, like, let's see, where do we write it? And then the model gets written to the file right here. So it's like So mesh right into packages 3D, and this would be the VRL model, and the actual KiCad footprint points to this model right here. So like KiCad mod is from the KiCad footprint generator. It's a library that allows you to create the footprints programmatically in Python, and in this function I generate the footprint. So the way this is organized is first I have the parsing part, which just calculates the default values, and then I have the generation part here in generate, which creates the actual KiCad footprint. And I like to organize it this way because it's really clear what the values are. So in the generation part, you may use the same value several times, and you really want to have a section here up front that kind of sets the values to defaults. So just from the width and length of the package, this script generates a default footprint. And we can compare it to the default KiCad footprints, and we can see that it's basically the same. And I'm doing the same for the surface mounted IC packages right here, where I generate a surface mounted IC with width of 6 millimeters across the chip with pins, and height of 1.75, and it has 8 pins, and it's normal board density. So let's go. Is there anything interesting about this? So when I also generate this custom footprints, I have gone for the rounded edges, because I've seen in the IPC somewhere that the recommendation is to actually use rounded edges for the packages, because it seems to like produce better results. About the board density, so KiCad doesn't normally provide different board densities, but it's very useful for placement. So if you look here, I have this border around the component, and this is set to normal board density, so there is 0.25 millimeters around the component, and it doesn't matter how big the component is, there's always 0.25 millimeters around it. And this is very nice in order to place the components close to each other and to align them visually. I would really like to see some functionality in KiCad where you could just move the component, and it wouldn't actually move the component if there is something in the way. So kind of like you could also have like a shove functionality where you can move a component and it would just like shove this other components around. But at the very basic level, it would be very nice if there was a function that would allow you to put the components next to each other and then just not move the component at all if there is something in the way. Let's look at this surface-mounted IC package. So KiCad provides a bunch of different surface-mounted IC packages, and there is one, I think, in like housings. Let's see, is there one in housing somewhere? This is kind of what I mean by, you know, that KiCad makes it very hard for you to find the right footprint. So like, okay, so this is a SOIC package. It's like a 5.3 times 6.2, but is that really the right one? Like, what does it mean 5.3 times 6.2? When if I go to like this, let's see, if I go to this chip, I'm just gonna go to the chip itself and the schematic, and I want to see. I just want to search for this in Mouser. So I search directly for the product number. So let's say I open this datasheet, and what do I see here? In the package section. So this is, let's see the size of the chip. Here it is. So this is like 6.2. Okay, Well, obviously then they mean the width pin to pin, but then like let's see if we go back to the right there. But then it's like 5.3. Really? Like, okay, so this doesn't seem to be the right package. Like 5.3, what would that be? 5.3. This is like this is just 5. So the length is 5. And that's like 6.2 is the width. But it's not really clear. And like I cannot pick this package because it's probably going to be wrong. Let's see what other packages they have. Like there is SOIC 8 3.9 times 4.9. So probably this is more correct, but it doesn't have the heatsink pad. Okay, let's go to this one. Okay, it has a heatsink pad, but I cannot really easily modify any other values here and get the footprint generated automatically for me. If I want to modify anything here, like even just setting the rounded corners, I have to open the generation script for this library, and I don't even know if this is generated with a script or if somebody just went in and designed this footprint manually, because the scripts that from the KiCad footprint generator don't come with KiCad, so you don't know where the library has been generated. So there's no easy way to like modify any of this. Let's see if there is any other one. There's one called Power. Oh, there's another one. Look, like Power Integrations SO8. Like, what the fuck? What is the difference? Let's see. If we place this one and then we go like and place SO8, let's place this one. So like, okay, this one is a little bit bigger, but there's probably like hundreds of other variations. Let's say SO, let's see, so let's place these ones. So this one is a little bit smaller. Okay, let's place another one. So this one is the same size as previous one, just without the power pad. And what others do we have? Do we have any others that are basically the same package? So to find the right package, you have to scroll through this long list of packages, and there is no obvious way to just describe the package with a string, which is like as simple and as straightforward as this IPC definition. Like, let's look at SOIC package. Let's see, small outline IC. Let's see, this one. So it's always 127 pitch, and the only things that are necessary here is the lead span, height, and pin quantity, and possibly the heatsink, the pad underneath. So the way that the pad underneath is defined, it's not actually in this cheat sheet for the IPC, but the way that it is defined is with like HS letters that come after the height and before the pin quantity. So if I open this spreadsheet again, let's see. Let's open the spreadsheet for the SOIC packages. So the way that I define this this heat tab is just with HS. So let's say I want to generate a footprint for, let's see. Okay, I'm just going to go through this first and see if I can find any other footprint that basically represents the same package. Oh, what the hell? Okay, I hope this is correct. Yeah, it seems to be correct because it's like 5, 5, 5. Okay. Single. ST power SSO. SO30. Oh, look. So then there is this TI-SO power pad and thermal VS. Let's add those two. Let's see. So this one is with a power pad, and let's add the one with the thermal VS as well. And that was actually different size. Okay, interesting. So what else do we have? I think that was it. I think that was it. Okay, there's like SM8. That's like a little bit bigger. Okay, but this is not an SO package. Like let's just stick to this ones. So this is the different variations of the SO8 package, and you know, the only one that is like different width is this one. But if you look at these different packages that represent the same SO8 package, they are, oh, I can't even like, okay, so it created, can I move this? Okay, so the vias come with it. That's really good. Okay, so this is just the variations of the SO8 package, and there are at least, I can see like, is this one the same? Okay, there is one, there is 3 different widths. I think this one is different width. Is it the same width? Yeah, that seems to be the same width. But okay, particularly I don't like having vias in the footprint, because it makes it difficult to like, let's see, I don't think we can even select this. There is a pad, but we cannot actually change the size of this vias. So those footprints are rather useless. But then we have 2 different variations. We have this one and we have this one. But then it doesn't say like, let's say I want to have a different board density, so I want to change this this border around the package, and there is no obvious way to do that in KiCad. Like there is no way to just enter a different number for this board outline and get the package automatically generated. Let's say I want to generate the package for this IC, which is 6.2 times 50. Or actually the length is going to be calculated automatically. All we need to know is the height. So the height is 1.7, so it's 6.2 times 1.70. So that will be 620 times 170. And then it's going to have a hits. Does it have a heatsink? Let's see. I think it does, yeah. So let's do HS9N. So with the heatsink, it's going to have 9 pins, so we say 9N there. And then we run the generation. And then we got a problem here. Oh, yeah. So I just typed it wrong. Typed different. Yeah. So had I looked in this had I looked in this template here, the cheat sheet, I could have seen that there is like a dash there. So like dash pin quantity. Okay. So now we should have the footprint. Let's add it here. So this is our generated footprint. If we place it over it, it's like basically the same. The only difference is if you look at the way that this mask around it is defined, the one that we have generated has a, like, it has exactly the same distance. So the one that we generated is the one that actually sticks out a little bit more here. Let's move this. Let's see. No, that was the other one. So I want to double check just that I got all of these things right. So here's the recommended one. Well, this is going to be correct because I based my generation on this. Right, so this is the solder mask. $295 times 490. But it doesn't actually have this the silk screen around it, so it's really hard to tell if this is correct. But according to the data sheet, it sticks out about I think 0.5 millimeter on each side. But this is both close enough, and this is much better because all I had to do to generate this footprint is just type in like a simple description of it, which is well defined, right? Let's see if we can find something that has a different SOIC package. SOIC 14. So suppose I were going to use this particular chip in a design, and then it comes to like assigning the footprint. Let's see if we can find a footprint for it first in the KiCad default libraries, or should I say like default template libraries, and then we're going to generate a footprint for it. So, like, where is the... Oh, there. Where is it? Like, where is the installation? No. Oh, this is something else. Oh, this is evaluation board. Like, what the hell? This is evaluation board. They just have a picture of a chip there. Can we search for like 74? I think those will usually come with. Let's see. It's like, let's just pick any one of these. $74 HC. Can we search for that? So this is SOIC 14. So let's say we have this datasheet and we want to add this component into our library, like the local project library, and then use it in our design. So can we find the right footprint for it? So now I would have to go like through this list, and I would have to search for SOIC 14. And then it's like 3.9 times 8.7, and it's all not well defined, so like you have to really look into this, like 3.9, 8.7. But okay, right. But 8.7 is not even like 8.65 or 8.95. By the way, so this length is not even part of the standard definition. You don't need to know it. You just need to know the number of pins. And then you know that it always sticks out around 0.5 millimeter on each side. It could be a little bit like plus minus something, you know, but it's usually around 0.5 millimeter. But then you have this reservation also that adds a little bit of margin around it. So let's see. This looks like a correct package, so we could use it. But then let's see how it aligns. Like, it doesn't really align with, let's see if it aligns with that one. Kind of aligns with that one, right? But then there is no easy way to kind of like, let's say I want to use a larger margin around it. I want to go for like this low density board. Is there an easy way to do that? Like, no, there is no easy way to do that. Let's generate 3 different footprints for like high density board, normal density board, and low density board with our scripts. So what do we have to do that? We have to generate a footprint for SOIC for 127p. So what is the width of this chip? 6. Yeah. So it's gonna be like 600. Oh, it's like 600 plus 0.3. So it's really a lot of tolerance there. So let's go for 6 millimeters times height of the chip is 1.4. Oh, it's actually 1.4. Is it? No, 175, right. And it has no pad underneath, so it's going to be 14 pins, and we have normal density. We rerun the scripts, and then we can go back here and re-add this custom footprint, or actually just add it side by side. So I could be typing this directly in the dialog where you could assign the footprints in the PCB editor, or like in the schematic editor. Like, I could be entering those names directly here, and then have a button somewhere that generates the footprints that are missing. I mean, that would be so cool. Let's close that and go back here. So this is our generated footprint. And it's basically the same as the KiCad one. The only thing that I can see that I've missed is the marking for the first pin. Let's actually go back and add it here. So we generate the silk screen here. So what we want to do is like add a line that adds marking for the first pin, and we can do that by just simply drawing a line from the beginning of the pin, like alongside the pin, the first pin, basically. So I'm going to put it here because I want to use the value that relates to the pin layout. So I'm going to add it after I've added the pins. And that would be a line, and it would go from x would be like minus. Let's see, that would be pad distance. So pad distance is the distance between, like, across the pads. It will be like from here to here, and the footprint is centered in the middle, so it's always centered in the middle, which makes it very easy to generate the footprint. So let's see, minus pad distance divided by 2. That would be like, the pad distance is the distance from here to here, so divided by 2 would be just a half a distance. So now we have moved to the middle here, in terms of the x coordinate. And then we will move half of the pad pad length, sorry. So now we would be here. And then we need to go in the y coordinate, we need to go pin start y. So pin start y is calculated as pin count divided by 2 minus 1 times the pitch of the pins divided by 2. Why is it minus 1? Well, because the distance we divide by 2 is like from here to here. And that distance is 1, 2, 3, 4, 5, 6 spacings. And there are 7 pins so on this side. So if we divide the pin count by 2, we get like 7, and then minus 1, we get 6, times the pitch, 1.27, we get the distance from here to here, and then we divide it by 2, so we end up like here. So this will be the start of the first pin, right? So it'll be pin start y, and then minus p pad width divided by 2. So now we are like right here, and then let's see, and then we're gonna subtract possibly like 0.7, or actually I could use something else here. I could use the body width, body length. So this would be a little bit simpler way to do it. So this would place the line just here and just as an extension towards this side. And then let's see, and the end is gonna be at the start x position, and then plus the pad width, I think, pad length, sorry. And let's see, and that would be minus body length divided by 2. So let's see how this works out. Cool. So now we've added that. I'm just a bit worried that it's like a bit too close to the pad. Let's see how close it is. Really? I think I just discovered something that was a little bit wrong here. So I see. So this is a process that I only have to do once. So as I'm like designing the schematic, I'm improving the script all the time. Once it's working and I know it's working, then it's going to be working forever. And then until I find some footprint that the script generates something else or just doesn't manage to generate correctly. So let's see. So what I want to do is see this 895 there, right? So if we go and we multiply this 895 minus 1.27 times, no, times 6. Right, so there's like 1.33. But then there is this. I wonder actually what that number means. That's the maximum. I think that's the maximum size of the chip, right? So usually it would be like 865. As you can see, it's like 1 millimeter. So it's like it's half a millimeter, sticking out half a millimeter beyond the last pin. So it's like half a millimeter from the pin center to the side there. And since the pad is a little bit it's a little bit wider than the pin itself, you kind of get like this thing ends up being a little bit too close to the pad. So what we can do is we can actually generate the silk screen, because silk screen doesn't really matter that much. It's just that it has to like look good, and it shouldn't enter like too close to the pad there. Let's see. The good part is that it doesn't enter into the solder mask. But look at this. There is a difference here. There is so much margin around this pin here, like the solder mask margin, and this is too much. This is a lot. I've seen in some datasheet, like I think for this particular chip that I'm using for this project, that the solder mask should be like 0.07 millimeters around the pin, around the pad. And we can easily add functionality to like change this. So let's say we want to add functionality. This is currently not in the script, so the script currently just calculates the default values. But we can easily like add for every single field here in the parser for this package. We can add functionality to just load the default from the CSV file if it exists, right? So let's see if we want to add, like we want to modify the solder mask margin here. So we have it as default 0.7, but we could also say like we want it to be set to the same value if it exists, or to be set to like 0.07. And if we then go to our spreadsheet here and we add solder mask margin here, and then we set the solder mask margin to 0.3 or like 0.2 maybe, and we rerun the generator, and then we can add a new footprint here that would be, let's see. Look, this looks more like their footprint. So you could easily change this, you know, and you can easily even like adding variations is really simple. You can add one with a like solder mask 0.2. So you can like obviously you have to change the name here. So you could say like you can always add text behind the standard name, and you can add anything because that's not going to be parsed. So we could say this would be SM02, and then there would be one that doesn't have that. And the generator has generated those footprints, and then we have this one would be the SM02. So if I try to add the same one, it's the same one that I've added there. But then if I go to the library and then I can select the one that has solder mask 02, And the good thing is that, you know, you specify solder mask 02 here, but this is like your custom text. But for the most part, the footprint has a standard name, and it's possible to generate the footprint automatically using default values if you just specify this standard name, which I think is the proper way to do it. It's like, it's just the way it should be done, you know. And then you have this solder mask 02. And you know, like when it comes to alignment, I can align things really nicely if I have using this courtyard around the package. But let's say I want to have another package, like I'm using board density that is like the low density setting. So with KiCad I wouldn't be able to do that. I would have to like copy this footprint and then modify it manually to account for the board density. I don't want to do that. I want to just go to the spreadsheet and I want to add a new variant here that is called like, let's see, that is called like M. And I want to like regenerate this footprint again, and then just go back here. Let's see. Come on. And just use the new footprint right away. So this would be the low density footprint, and as you can see, the courtyard around it is like a lot bigger. But KiCad does not support it by default. This is only like doable with an automatic footprint generator like the one that I've just designed here. So like, and you can do so many different variations. It's like once those scripts are working, and once they're working properly, and once they have been like thoroughly tested on real designs, and the more boards I design, the more I'll like fix bugs in them. Like, once they're thoroughly tested, this is like the perfect way to generate footprints. And I don't like this margin that is so big. Let's see, how does this work? I just want to double check something. Okay, so this is the keep out area, right? It kind of, it can push the track as close as this keep out area, but not beyond that. And if I were to use the default footprints, then my keep out area is precisely, it's even a little bit bigger than the solder mask. And here, like in the corners, like what the hell? Why is there no solder mask in the corners here? This is really bad. Like if I have a track going there, it's going to be exposed. Okay, so this is my new way of generating footprints, and I really like this way of generating footprints. I'm going to be using it more and more, I think. I just want to be able to enter a standard IPC name and get the footprint generated for me. So in the current version of those scripts, what do we have? Okay, this is actually old because I haven't modified the BGA generator to use the new parsing functions, and I haven't actually rewritten it to this clean format. But I can generate right now. I can generate chip capacitors, chip resistors, like chip diodes. I can generate molded components, which are diodes and inductors. Let's see. And there are, yeah, and also the tantalum capacitors, both and polarized and non-polarized capacitors. And I can generate the SOIC packages. But as you can see, it's fairly easy to like add support for other packages, and that's what I'm going to be doing as I go through like more designs in KiCad, and as I need more packages, I will just update this those scripts to generate them. And I think this KiCad footprint generator project is a really good project, but the only problem with it is that it doesn't standardize the way that it generates the footprints. It doesn't allow you to specify the footprints as CSV files. It just has a lot of scripts. It just has a lot of different scripts that just, you know, that all name different things, and they're like what the hell? And also like choke, Schaffner, RN, whatever. Like the only reason you ever need to generate things manually like this. Let's look at what this is. Like, what is this? Can we find that choke somewhere? Like RN202. Does Mauser even have those? Schaffner, right. This is like a new product. Oh, it's like a okay. It's a through-hole component. IPC actually defines convention even for through-hole components. So it's not just for the. Oh, look here. So this is the suffixes, the standard suffixes, and HS that we've used. It's like a landing pattern with heatsink attachment requiring additional holes or pads. And there are different like variations here. So like alternative components that do not follow GENEC, EIA, or EEC standard. And M is like most material condition, nominal material, and least material. And then for like custom components that are very like customized for the manufacturer, you just name them as using the manufacturer part number. And this is the naming convention for the through-hole components. So imagine you could just, you know, type this in. So you just look at this cheat sheet, and when it comes time to assign footprints, or when you're creating your project library, and you want to assign footprints as you go, as you pick your components and go through the data sheets, like, oh, imagine just having to type a name that describes the footprint. So you know that like for a dip package, it's going to be like lead span, lead width, pin pitch, body length, component height, and pin quantity. And you just need to learn this once, and then you just use the same template for every single package. Let's see what else they have here. So let's see, this is like Barnes. But is there any, like, where does it actually generate this from? Okay, so let's look at this Vishai stuff. So it's like 4825. So this is the only component. It's really non-trivial to like, if I want to add a new component, what do I have to do? And why is it like, why does it have to use like the manufacturer name when it looks like it's standard footprints? Like why? Let's look at this one, 4825. Let's see if you find it. Oh, wait. No, let's go here. Actually, I'm going to keep that page. I'm going to go here. So let's see. This is this looks like dimensions. Let's see. This is like a molded component, so this is not a chip component. You would usually use, like, for components that don't have pads that go all the way out, you would use like a molded component template. So let's see. 1372, is that what they're using here? Right. 4825 is the footprint name. So it's like 4825. Do we see any 48 here? 48. Okay, that will be the length of the whole thing. 48 and 25 is the width of it. Yeah. So what would be the name of this package if we were to generate it using our generator? It would be like, let's see, it would be 121. So it's like 12. Is that 12 millimeter? Is it really that big? Like, it's huge. Like here he uses like, okay, wait, let's see. 1219, but this one uses like 1372. Where is 1372? There is not even the number here. Like, where does it take 1372 from? Where does that value come from? Like, what the hell? So let's say we're going to generate this package. So it's going to be 121 times 0, 63. Let's see if the generator can actually generate this package. Like, it could be that it doesn't generate it. Let's see. And the height is 57. So what I'm gonna do is I'm gonna generate this footprint and I'm gonna compare it to their default recommended footprint. Oh, didn't I add that library, like molded capacitors? Let's see. This is one of the other things that I really think should be improved in KiCad, is that it should just load all the libraries it can find in the KI sysmod folder. Like, I shouldn't have to add the libraries manually here. So does it look like this? Let's see, 16.7 across. Yeah, a little bit outside. Ours is a little bit smaller, but then you have to understand that it's like 13.72. The component width is 13.72. So it's like there's plenty of space. The component is gonna go like this. Let's see. Oh, it actually has it's 1372 with those little like half balls there. But it's 12.19. Also, I think I found a little bug here in my molded component generator. I never actually used it for the capacitor stuff. But the silk screen should always be the size of the package itself. So I'm gonna go and fix this. So in our molded component, let's see what the silk screen size is set to. So let's say if P type. Oh no, this is actually this is the old stuff. We don't need that. Let's make this actually let's see, body width. So pad width and body width, maximum of those. No, we'll just do like this. We'll just do body width. Because this is silk screen, this is not the manufacturing lines. And body height. Body length. Let's see if this looks different. Yeah, this looks better. So this is what the actual footprint looks like, and this is the size of this capacitor. Now look at let's look at how much it is across. So it's 5.58 across. Now the pins are you don't actually specify the width of the pins in the IPC name, so it's kind of like you could pick default values, but if you need to specify, you really need to have the way a way to do it. So let's see. The recommended width of the pad is 5.58, which is clearly more than what we have. So like 3.52. So we want to make the pads bigger. Let's add support for that in the script. So I'm going to go over through every single field in the script, and I'm actually going to add a possibility to specify things directly in the CSV file. But since this is something that I haven't added yet, I'm just going to add it for this particular field right now, and then later I'll go over all the fields and do the same. So let's see. What we want to modify is the pad width. So we want to do like this. We want to set the pad width. Let's see, body pad width. Let's see. So if we do that, and if we set body pad width to 4.32, and then use the default rule, so 4.32 times 1.1, 4.7, right. So we probably want to specify both, like body pad width. It will be useful to specify body pad width if we were to generate a 3D model later with the actual pads. So if we were to generate the molded component model with more detail, it would be useful to specify body width as well, like body pad width, and that would be 4.32. So let's put this here. So basically for all the fields, I would just have to change it to use the default specified value in the CSV file, or to calculate it using a rule, like a default rule. So let's close this, and I'm going to open the capacitor, the molded capacitor file. Essentially the same one that I had open here, like this one. But I'm just going to go and open it in the spreadsheet viewer. And then the pad width we specify as 5.58. So we can actually specify very exact values here. We don't need to like use the standard precision here, which is like 1 decimal point. We can specify precise values if we have them. Like that. And then then it becomes kind of like a custom component. So we can do like, we can say can we get this number here somewhere? I want to know if that is the real manufacturer number or if that is something else. Okay, this is the real manufacturer number, so we can use that. Or should I actually use that? Because it's likely that Vishay has many more components that kind of follow the same pattern. So we could just call it something really simple, like let's add just like Vishay there. So oh, let's see. I need to pad width, okay. So when I'm going to be adding this, I also need to kind of make sure that that those fields actually exist, even if they don't exist in the CSV document. Body pad width, come on. Oh, right. This is because this is generating for it's using the same file for generating. I think could it be molded diodes, and that file doesn't have body pad width in it. I started working on a little like file here, like let's see, prop. I'm just gonna write a simple function like this is just to make it work. So return self props name, prop or default. Let's see. Yeah, we're gonna have to do it for both. So later, most probably what I'm gonna end up doing is kind of like inheriting this class from a like component model, and then having all those functions built in. This is really not the best way to do it, but this will have to do for now. Oh, right. Let's see. What is the problem here? Can multiply sequence by non-int of type float. A sequence. Like, is default like a default? No. Okay. What sequence? Like, what does this end up being? Like, print, let's do this. So it generated the diodes which didn't have those fields, but then it was like, so did I do that correctly? Let's see. This should convert to a float. Ah, I see. So for the components that don't have that, is it gonna not work? Because we need to rewrite this a little bit. If name in props and yeah. Courtyard. Let's see. Key error. We don't have courtyard key. We don't? Didn't we calculate the courtyard? Okay, we didn't specify the density, or did we not specify the density? Yes, we did. Okay. Interesting. Let's set default. I have to find out whether it doesn't work. Wait. Okay. Why did I print that? Oh, there. Okay. Let's go back to KiCad. Okay, that didn't work, apparently. Are we not generating this stuff properly? Like, what the hell is going on here? Come on. That looks like a bug to me. So cap MP 8170X15M like does not have courtyard key. Why? What the hell is going on? What the hell is going on here? Come on. Let's see. Let's see what we end up with here. Oh, right. So it is actually in the parsing that we fail. Right. So it's 4. Okay. Oh, this was wrong. This got copied from a different. Yeah. That should work. That's the thing with copy pasting. Like, this doesn't work either. Okay, let's see. Are we not returning the right thing here? Really? And what is name then? Let's see. It's supposed to be set to like pad width, like body pad width, etc. But for some reason it's not working. Yeah, body pad. Oh, it is working. There it is. Yeah. And pad width, body pad width, and pad width. Did I specify the wrong value in the CSV? Body pad width. I'm supposed to have that. But I only have body length. And I have body pad width there. But only for inductors. Am I doing something wrong here? Do I only have body pad width for inductors? Yeah, it's gotta be here. 4.32. Pad length 4. So this is supposed to work. Let's see. How can I check this? Ah. I think it's like this. Let's see. Can multiply sequence. But is it a sequence though? Like, what kind of sequence is it? Why is it a sequence? I don't usually use Python in my work. I only use Python when it's like really necessary. Let's see. Pad width. Body pad width. Let's print this out. What do we get? We get an empty. We just get something really empty. Okay, let's do like this. Let's move this here. Can we get it to work like this? I don't want to have it in that file. Oh, that's gonna be like prop. Okay, so why is it saying that it's a sequence? Pad width is empty. Oh, right. So it's parsing actually the one that has like an empty string. Yeah, I'm gonna modify the parser here, like in the generic file. So if it's, let's see, except, and then we can do like if row I not like can we do this? Yeah, that seemed to work. Okay. Did we actually get our footprint now? No, we didn't have the footprint. God damn it. So we're not actually getting the right values here. Why? So default should be like print, let's see. That's key error. You know what? I think that the proper way to do this would be to like define, make sure that all of these are defined, and then just use like the or expression. But this is like let's see. Can we get this? Let's see. Can we get this like this? So it's supposed to be 432. Like every time it's called, it returns 432. But then why the hell? Oh, wait. We changed it to Vishai, so we have to select Vishai here. There we go. It was already there. I was just selecting the old one. So now we got the new footprint here. That took a bit of time, but you know, that was just like figuring out small details like in the generation process. But from now on, all I have to do is just go to open the spreadsheet and just enter the precise values for these two fields. So I'm going to modify the code. I'm going to actually refactor all this stuff again and make sure that we can actually always do this. That we can always set custom values on all of the fields, right? So we should be able to just specify any of these fields. But I need to make a few changes to the code for that to work. Let's see. So this one is going to be pretty much like the one in the datasheet. So this one is let's see. Did we specify the width of this 457? Let's see. This dimension doesn't really matter that much, but we can specify that custom as well. So it's close enough. And this is 565, like 556, 552. So that almost like 538, yeah. I was just measuring it from, I have to measure it from the pad, not from the like solder mask. Yeah, this is gonna be exact. I mean, we've just specified it, 532, yeah. Okay, so easy way to add new footprints. Like if those scripts are available in KiCad, or at least like a function, just pop up a dialog and just generate a footprint from the definition, and maybe possibly like specify custom values for some fields. Like that would be so awesome. Okay, I'm gonna go ahead and turn off this stream, and I hope this was interesting. And in the next series of this power supply board design, I'm gonna root the board and then send it away to manufacturing.